Buongiorno a tutti, partiamo, poi chi si collegherà parteciperà comunque. Buongiorno a tutti e bentrovati. Benvenuti al quarto ed ultimo appuntamento della serie web, organizzata insieme ad Aanderaa, produttore leader di strumentazione oceanografica, di cui siamo distributori in Italia. Oggi saranno confrontati 3 sistemi per la misura di onda e corrente. Potete porre i vostri quesiti nella chat ai quali risponderemo al termine della presentazione. Nei prossimi giorni, come sempre, riceverete un'email contenente la presentazione e la relativa documentazione. Nello stesso email saranno disponibili i link per accedere al materiale dei precedenti webinar. Io sono Linda Croci, il nostro relatore è il Product Manager di Aanderaa, il dottor Anders Tenberg. Hi Anders, welcome.
Buongiorno, buongiorno.
You can start with the presentation.
Thank you. So I share my screen. Can you see it?
Yes, I can see
Linda?
it.
Yes. Okay, good. Yes, so welcome to this webinar and thank you for attending. And this will be about measuring waves and currents and features to think about when you're planning such measurements. And the agenda for today's presentation is that I will talk a little bit about 3 different ways to measure waves as we offer from Aanderaa, and what type of transfer functions we offer, because if you measure with the buoy, you must translate the movements that you measure with the accelerometer to wave information, and the same thing if you measure acoustically or if you measure with pressure. Then I'll talk a little bit about the noise reduction that we have implemented into the Motus buoy sensor for directional waves, about the new methods that we have developed for acoustic wave, directional waves, pressure-based wave sensors and how that works, and then I show you results from intercomparisons that we have done between the different types of sensors. And then there will be some things about measuring currents from moving platforms, from buoys and moored platforms, and in high sea state, and then some things about some summary and possibility to ask questions. And please, as Linda said, if you have questions, also put them in the chat during the presentation, and we will answer them at the end of the presentation. So at Aanderaa, we offer 3 ways to measure waves. The first one is from buoys. It's a accelerometer-based method, and here you need to translate the movements that the sensor is measuring into wave information. And here you see the functions that we use to do that. I will not go into details about this. We have several papers have two scientific publications which goes more into details about the algorithms that are used and how these are implemented. So basically you translate movements at the surface on a buoy to wave information with such algorithms. And then we have the orbital movements that you use to collect information acoustically about the directional waves. So what you need to do here is to go as close as you can to the surface, still considering that if you go too close you will have contaminated zone with not so good information about the orbital movements from the waves. But you need to go close and then try to measure the orbital velocities in 3 or 4 directions, and then you can calculate the directional waves. And the algorithms, mathematics behind this you can see here. And we also have a white paper about the acoustic wave which you will get sent to you after this presentation. Then we have the pressure fluctuations, which are also used then to measure waves. Then you don't get the direction. You measure the pressure variations at the bottom and you get, or below the surface, and you get information about the wave height, wave period, wave steepness and things like this. And the transfer functions we use here is presented in these equations here. So with our motor sensor, the accelerometer-based sensor intended for buoys or surface platforms, we have implemented unique possibilities of filtering the data, because if you want to measure waves, regardless if you use accelerometer-based or pressure-based or acoustic method, you need to have good ways of reducing your noise. Imagine, for example, if you want to pick up waves with a wavelength of up to 30 seconds, for example, on the surface, there will be a lot of noise coming from the smaller waves and from movements of the buoy in the sea. So we have implemented mechanical filters. Basically, it's a metal plate that we have included in the sensor, which mechanically dampens and takes out the high frequency noise when you do the measurements. And here you can see what on this graph here you can see what the filter is actually doing when we filter the waves. Here this is laboratory experiments just to show how it works. The red here is the true values without noise. And blue is what you measure if we don't implement this filter capacity. So a lot of noise you introduce, but with the filter, with the mechanical filter, we get a curve which looks like this. And then we also have possibilities with this sensor to do electronic filtering of the signal, and that gives good quality of the wave measurements, as we will see later on in this presentation. So the motors has been used a lot in different projects, and mainly the most frequent projects have been on navigational safety. And here we see one example of that. Typically we provide buoys which are for navigational purposes, painted for navigational purposes, so they can be included in the network of navigational buoys, and then they are equipped with sensors to measure waves, but also, as you will see, to measure the standard is waves, meteorological parameters, and currents. And here is an example where the Norwegian Coastal Administration have deployed such buoys along the coast of Norway, and data, of course, in these applications is transmitted in real time. So in 2019, a new Norwegian cruise ship was cruising along the coast for its maiden voyage, and it had about 1,500 passengers on board, and they didn't look so much into the information of waves along the coast, but our systems were measuring 18-meter waves at this time, and all the 4 engines on the ship stopped because they didn't have enough lubrication because of the movements in the waves, and the ship started to drift towards shore, and they throw the anchor. You can see it here, and about 200 meters from the shore the anchor was holding, so it never went up on this rocky shore, which would have been a catastrophe for this new ship. And the Norwegian Coast Guard started to evacuate, so they managed to evacuate about 500 people before the engineers on the ship managed to start the ship again. So if they would have listened a little bit more to the navigational authorities, which were warning for, they were measuring 18-meter waves at locations south of this, but where this ship passed, it's known to have these interferences between the waves, and you can easily get about 30% higher waves at that place. So these systems, the standard equipment on these systems is directional waves, it's currents, and here you can see normally we equip the systems with two buoys, with two current meters, one to measure surface current and the other one to make a profile below. So they are placed in a rack, and they are included in a moon pool, a PVC tube which passes through the buoy hull. We the standard buoy have two moon pools, one for current measurements and the other one for environmental measurements, if that is desired, and I will show you some examples of this. So standard buoy is directional waves, currents, surface currents with this one single point sensor which is pinging through the PVC tube here, and an acoustic profiling sensor below. And then meteorological sensors. Here we integrate sensors from third-party manufacturers, typically from GIL or from Vaisala. And other systems like this for navigational purposes, for example in Spain, Puerto del Estado, outside the port of Cartagena. And here is another example. This is from a port in Brazil, where they also use the same type of setup. We have also delivered many of these buoys for other applications which are not navigational purposes, and here are two examples. Still they use the same type of buoys, but normally then they add water quality, and then typically we integrate the YSI EXO sondes. YSI is a sister company from us to Aanderaa, the same group Xylem, and advantage here with the water quality sensors here is that they have anti-fouling inbuilt with the wiper and copper nickel guard. So these buoys are used by major dredging companies, Dutch and Belgium, and then also several of these are used in aquaculture. This is an example from Tasmania for salmon aquaculture. And recently, or since 1 year back, we are also selling Motus buoys for integration to other types of platforms. We wanted to gain experience first from many systems delivered, how well it worked in different situations with different anchoring solutions and so. But now we also sell these type of solutions, the motor solution and the current meter solution, for integration into other platforms. And here we have examples of bigger platforms where Motus and current sensors are integrated to. This is the 10-meter diameter buoy, which is in operation in the East China Sea from the Chinese Meteorological Institute, and where Motus is placed inside the hull here. One unique feature with the Motus is that it has inbuilt features which makes it possible to place it off center and at different locations on a buoy and compensate for that with the factors. So you can put it on basically any system we can see, and by using the settings to compensate for the non-ideal movement and the off-center placement of the sensor, you get also high quality data from other platforms than ideally moving in the waves. Of course, a big platform like this will not pick up the really big waves. Now we are delivering motor systems also for even bigger platforms, some which are for oil, where oil tankers dock and fill oil, and they are something like 30 times 30 meters big, these platforms. And also on small platforms they are used. For example, here it's a wave-driven platform, Autonaut from the UK, where several Motus sensors have been used to measure directional waves as it's moving through the sea. And also now we are making trials on sail buoy, which is just 0.6 meters long, autonomous and wind-driven. We also have Doppler current sensors on these platforms, and they deliver good high-quality data. So now we move to the acoustic way of measuring directional waves. And here at Aanderaa we have adapted our own technique, which we think works well. We have seen that from a 1 year test deployment, and basically what we do here is that we collect wave data acoustically. We try to go as close to the surface as possible, and to go close to the surface we use a pressure sensor on the instrument. It's not only a pressure sensor, it's a wave and tide sensor. So when you do the acoustic directional wave measurements, you get also pressure-based wave measurements as a verification of the quality. So you get dual wave measurements from the same instrument. And at the same time, this pressure measurements from the wave and tide sensor, pressure-based wave and tide sensor, is used to locate how close you can go to the surface. So we collect acoustic information from the wave movements, from the orbital movements in 4 directions. And the unique feature that we have implemented here is that the instrument, when it's measuring waves, automatically switches between different acoustic modes. When waves are small and the orbital velocities are not so high, it's only some centimeters per second, we use what we call ultra broadband. It's a broadband pulse with a long silence time in between the double pulses. Broadband, it contains much more information. It's like, narrowband, it's just a single frequency, while broadband, you are chirping. You are changing the frequency, and by sending out a signal which is changing the frequency, it contains much more information and it gives you more possibilities of measuring. But also it has disadvantages in some occasions, and I will show you some example of that. But for small waves, the system is using ultra broadband. Then when waves becomes a little bit bigger, about 2.2 meters, then it shifts to normal broadband, which the instrument uses also to measure currents if you set it up to measure currents with broadband. And then when the waves becomes even bigger, it automatically switches to narrowband. When the waves are bigger, the orbital velocities can go up to 2 meters per second, and then narrowband is the most appropriate way to measure the orbital velocities. And here you can see an example of how an instrument is switching between narrowband and broadband and ultra broadband. We see here the different, if we look at the violet curve here, we see to start with, it goes with small waves, 1 meter waves, it goes in ultra broadband, then waves becomes bigger, then it goes to normal broadband, and then waves go up to above 6 meters, and then it switches to narrowband. The customer or the end user doesn't need to decide what to use, because the instrument automatically is switching between these two to adapt to the best possible method. So here we see wave measurements with blue is significant wave height measured acoustically, and the yellow is significant wave height measured with a wave rider, a buoy from a Dutch company, which is considered to be the golden standard. And we also have a wave sensor, a pressure-based wave sensor, which is orange. So you see that they track quite well. So at the same time as you measure the waves, you also get current information from, it's using free cells to measure the orbital velocities. Then you also get current information from these free cells, and then in between wave measurements, the instrument can measure then full profile for currents. The pressure-based wave and tide sensors, they can log time series of pressure variations at 4 or 2 hertz, and that makes it possible then to calculate wave height, wave period, and wave steepness, and all the wave parameters except the directional wave. And we have had these sensors for more than 10 years now, and we have recently updated them to more powerful algorithms, which makes it possible to detect small waves, centimeter waves, from 40 meters depth. So we have pushed the limits here for what is possible with pressure sensors. Before that, to measure small waves, you had to go relatively close to the surface. But here now we can detect smaller waves. And here we see examples of trials that we have done from 35 meters depth. Blue is with old algorithms where the sensor barely picks up, these are small waves, but the yellow is with the new algorithms, and then you pick up all the waves, small waves that you have at the surface from this more higher depth, water depth. And this was placed, this was in a fjord and placed on a string above an instrument. And these sensors are used in many different applications, both to measure waves and tide, and also in seismic operations to measure millimeter movements of the seafloor, as well as, for example, here in offshore applications. We have some companies that use more than 200 of these pressure sensors to survey oil wells and look at if the wells are, if the seafloor is moving, and they need millimeter resolution from 1,000 meters depth. They look at if oil wells are moving or collapsing or so, then you must put more water into them. And if we compare the different methods, if you want the highest quality of waves, if you want to distinguish between swell, the long waves, which comes from far away, and the shorter waves, which are wind driven, then you need to measure from a buoy, and you need a accelerometer based, or you need a motor sensor on a buoy. Acoustic wave measurements gives you a lot of the same information, the directional wave information, and most of the wave parameters, but it's not able as of today to distinguish between, for example, swell, which comes from a different direction compared to the wind-driven waves. And then the wave and tide sensor, the pressure-based one, gives you only wave height and wave steepness and wave period and so. So how do these systems compare if you deploy them for a longer time period? We have done in total about 2 years of test deployments, continuous, before we start to release the systems. The motors came earlier, but the acoustic wave was released only about 1.5-2 years ago. And we deployed systems here off the coast of Norway, and we can see the systems here. Here is a buoy with a Motus sensor and with current sensors on it. Here you see the Motus sensor. We had several Motus sensors, some placed in the center, some placed off center, to see how this compensation possibilities of off center was working. And then we have the acoustic, we have a bottom frame with acoustic wave measurements using this Seaguard 2 instrument. And on the Seaguard 2 instrument we have the wave and tide sensor, which detects the surface and also gives you wave independent pressure-based wave information. And as a reference, we always use the wave rider buoys, because they are considered to be the reference for accurate wave measurements. And if we look at in general on all the measurements that we have done, the results from the different methods compare very well. Here we can see, for example, the wave height comparing the acoustic wave measurements with pressure-based wave measurements. Here we see energy spectrum from wave rider for a certain period, and here we see energy spectrum from the acoustic wave for the same period. And here we have Motus, the frequency plot for Motus, and the wave height here for acoustic waves and for Motus. And here we have intercomparison between the different systems. Number one is significant wave height for the Motus and for the wave and tide sensor. Number two is for the wave rider and the Motus, and number three is for the Motus and acoustic wave sensor, and number four is acoustic wave and pressure-based wave. So in some case, for example, pressure-based wave is a little bit more noisy, but in terms of giving similar results, you can see that they correlate very well. and also in wave direction. Here we have wave direction from acoustics, from Motus, and from the Wave Rider compared. And 1 year deployment here with the Motus sensor. We can see features. This is just month by month. I just show you some features. The colors here, red is longer peak period, so here we have about 20-second peak period. So we have long swells coming in here, also with higher waves. The further out you are on the scale here, the higher are the waves. But here we have long swell coming in and so we can distinguish between the long waves, the swell, and the wind-driven waves. And this is when you have between Iceland and Norway, there is an opening, and then these long period waves are moving in like this during certain times of the year. Then we look a little bit at measuring currents from buoys, and this has been considered traditionally to be a little bit difficult in terms of quality, because you need to compensate every single ping, acoustic ping, for movements. So you need accelerometers in your current sensors, which we have and which we have had for many years, also in the previous generations of current sensors. And I told you our current sensors, they can operate both broadband and narrowband. This is automatic when you detect waves, but it's user selectable when you deploy your instruments. And here we can see advantage of operating broadband and narrowband, or operating broadband. Broadband, since the pings contains much more information, you need to send out much less pings, acoustic pings, to get the same high quality data. This is measurements in a fjord, and the instrument was placed at 35 meters. So the depth is here from 0 to 35 meters. And on this axis here is time. And the scaling here is the current speed. It goes from 0 to 60. We can see that the speed is very low here in this area, except close to the surface. The surface is here. And what you see here in the other plot below, it's the noise of so it's the standard deviation on the current measurements for the same measurements. So by having broadband with 50 pings, you get low noise. If you switch to narrowband and 100 pings, so double number of pings, you get much more noisy data. And actually, to have the same information in narrowband as broadband, as 50 pings in broadband, you need to ping 1,200 pings with narrowband, but that costs you much more power. With broadband, and internal batteries, you get 335 days of measurements if you measure at 10-minute interval, and with narrowband, if you want the same with data quality, you get, instead of 335 days, you get 51 days. So more power consumption for the same data quality from broadband, from a narrowband. But if you're working from a buoy, deploying from a system which is moving a lot, like a buoy which is hopping up and down in the waves, or from an autonomous vehicle, for example, then broadband is not suitable. It gives you much more noisy data. And here is an example of that. This is current data. Time is here, depth is here. It's a Doppler current profiling sensor looking downwards. So you see you have a range of about 70 meters in this case. First, we use narrowband, 300 pings, and the data quality the noise level is low. And you can see the speeds here. The speed scale here is from 0 to 200 centimeters per second. Then we switch to broadband, and then data becomes very noisy. And this is because in between that you send out the pulses and they return, the sensor has moved. And that gives you what we call ambiguity problems. And these ambiguity problems give you noisy data. So on all applications where the sensor is moving a lot, we recommend absolutely to use narrowband instead of broadband. And then we switch back to narrowband, and then we get the same quality of the measurements again. And you can see here, this is the first cell closest to the sensor, to the Doppler current profiling sensor, measuring the currents. You can see with narrowband, you resolve all the details in a completely different way compared to broadband, where data is much more noisy. And then here, switch back to narrowband again, you start to resolve details again. And how does current measurements, how can you measure currents in really high sea states? Yes, I think from the deployments we have done off the coast of Norway now for 2 years, we can say that this is absolutely no problem if you compensate every single acoustic ping for your movements, and also you compensate for the rotation. And what we have here is an example of that. This is from from several buoys which were deployed in parallel. We have the same system here: surface currents measured by a single point sensor, and then currents below the buoy going down to deeper depths with the profiling sensor placed one above the other and placed inside this PVC tube for protection. And we can see here during this period here, we have wave heights measured with 2 wave sensors on 2 buoys, 2 motor sensors going from 1 meter wave height up to 7 meter wave height here. And then at the upper graph here, we see for the same period currents measured by 2 single point sensors on 2 different buoys, which are separated by about 250 meters. And you also have the first cell of the Doppler current profiling sensor from one of these buoys. And we can see that in most cases here, the 2 single point sensors, which are blue and black, they track very well. There are some small differences, but they are 250 meters apart. And most of the time, the first cell, which is about 4 meters below the surface, while the single point measurements are about 1 meter below surface, the first cell of the Doppler current profiling sensor compares well with the single point ones, but in some cases there are differences. And of course, this is because of sharing of the currents, and you have different currents when going deeper down. But basically what this gives you, since you're using 2 sensors, one single point with a high frequency and one profiler with a lower frequency, 600 kilohertz, you get an independent quality control of your profiling sensor, at least for the first cells here. If they compare during most of the time in many situations, then it's a good indication that the quality of both these measurements are good. And you can also, we have done on an observatory that we have been running at the University of Gothenburg. I also work a little bit there with oceanographic science. An observatory on the west coast of Sweden in the Koljefjord. We have been running this for about 10 years now. This year we will take it up because no one wants to use the data anymore. All the modeling work has been done for the area. Here we see some pictures and we see the location. It's a fjord, a closed fjord with low currents. And here we did some experiments to see how good is the quality of your profiling measurements and how can you get automatic quality control of your acoustic profiling measurements in real time. So what we did in this observatory is placed in a fjord with at 40 meters depth. It's using the acoustic profiling to get currents and backscatter information and mixing information in the water column. And then we have a string of sensors, mainly salinity, temperature, oxygen, and turbidity at different levels here above. And what we did, we placed a single point Doppler current sensor about 35 meters away from the profiling sensor. And by doing so, we get in real time an automatic quality control of how good the profiling data is at that it's at the same depth level, of course, as you have the single point sensor. And the single point sensor, they are more reliable because they have a better defined volume, and we have also a lot of tow tank tests that proves the quality of these sensors. So we can look here on the absolute current speed. The blue is from the acoustic profiler, 8 meters below surface. Red is from the same level with the single point sensor, and here we can see that they track well in terms of speed. Then if we look at vector speed along the fjord, so it both takes into account direction and speed, we also see that they track well during this period here. Below here you can see how the instrument is rotating. This is the heading of the instrument. But then during a service we dropped the profiler, and one of the transducers came loose, and that gives much more noisy data on one of the transducers. And by comparing now, again, we didn't do it by purpose, it was just accidentally, but we could see then that the quality, the comparison is not so good anymore. We can see in blue here the same cell for the profiler with one of the transducers was noisy and not working so well. That takes up the average speed. Noise in the transducers or in the acoustics gives you higher average speeds, and the background speeds here are low. And but without the quality control from the single point sensor, you would never have been able to discover that in many situations here the current speed, average current speed, is actually a factor of 2 higher than what is real and measured by the single point. And also because one of the transducers gives more noise, it also introduces directional error, as you can see here. So to summarize the presentation today, we at Aanderaa offer 3 ways to measure waves, and I've shown you the different systems and how they compare when you deploy them side by side. We have also deployed Motus buoys in very small, where there are very small waves inside fjords, and compare with the wave rider. And when waves are really small, normally the limit for our navigational buoys is around 5 centimeters. Then the wave rider better picks up the really small waves. We use innovative solution for the acoustics, where we switch between broadband, narrowband, and ultra broadband to get the highest quality on the acoustic directional wave measurements. And I showed you comparisons between the different technologies that showed that they agree well. And current measurements from platforms, even in really high sea state, we have sea states of up to 21 meters. Still, the current measurement seems to work well, but it requires that your sensors are able to compensate for every single ping that they make. And from platforms that are moving or vibrating, we absolutely recommend to use narrowband, because the quality becomes much better. With broadband you get ambiguity issues. And finally, I show you one slide of some new technology that we will be releasing this year. We will be releasing a new turbidity sensor, 6,000 meter rated and with a range from 0 to 2,500. We will be releasing a much higher accuracy conductivity sensor, and we have for the deep water oxygen optodes new types of foils, which are already used since many years on the shallow water ones, but which are more stable. And we already released this centimeter wave detection from higher depths from the wave and tide sensors, and also some features for anti-fouling with optodes, oxygen, and conductivity with inbuilt UV anti-fouling. So with this I would like to say grazie mille, and maybe you have some questions.
Thank you, Anders. Se ci sono domande potete scriverle in chat. Thank you Anders, again, grazie a tutti della partecipazione. Siamo quindi giunti al termine di questo breve ma intenso percorso. Speriamo come sempre di poterci vedere presto dal vivo con eventi, seminari che non mancheranno. Mi raccomando, per chiarimenti, richieste di offerta, approfondimenti, domande, non esitate a contattarci. Anders, thank you again. I really hope to see you in person in the near future.
Yes, you were talking about Palermo in the autumn.
Let's see, okay?
Yes.
No
Yeah.
spoiler.
No? Ok.
Grazie a tutti e buona giornata. A presto.
Grazie a tutti. Buona giornata.